This is Knowledge Engineering with Semantic Web Technologies, Lecture 3, Ontologies and Logic. Today, we want to talk about the foundations of logic. So what is logic and how is the meaning, the semantics of logic defined? So first, let's recall what we understand about an ontology or what an ontology is. So we had this nice definition according to Gruber. An ontology is an explicit formal specification of a shared conceptualization. And besides all the other terms for mathematical logic, of course, the formal specification is, of course, really important because this means we have a formal machine-readable semantics, which is expressed with the help of mathematical logic. So, therefore, today, we want to recapitulate what is beyond or what are the foundations of logic and why can it be used for exactly that purpose. So, for that, of course, we have to define logic, and there are many definitions, and for our course, let's stick to that one, so that's the definition for our lecture. Let's consider logic is the study of how to make formal correct deductions and inferences. So this is absolutely important simply because we want to deduce or we want to infer new knowledge from existing knowledge. So therefore, logic again is the study of how to do these things. So how to make formal correct deductions and inferences. And why formal logic? Yeah, sure, informal logic would not be any helpful. We want to enable automation, which means machines should be able also to draw correct conclusions, and therefore it must be formal. So this is the definition of our logic and of course the formal logic. Yeah, and of course this idea is rather old. So maybe you know that guy. This is Gottfried Wilhelm Leibniz, one of the greatest mathematicians of all time. So besides inventing calculus, besides Newton, of course, there was a long dispute between both of us who was first to define calculus. He also had the idea of automated reasoning. So once in a letter in 1687, he wrote, "The only way to rectify our reasonings is to make them as tangible as those of the mathematicians, so that we can find our error at a glance, and when there are disputes among persons, we can simply say, 'Let us calculate,' without further ado, to see who is right." So he already had the idea somehow to express natural language with the help of something like a formal logic, simply to solve disputes and to solve arguments. So that's quite nice, and this is something that we also want to do. We want to mechanize reasoning in that sense. Okay, so let's define logic. First, we have to talk about syntax of logic. Okay, but syntax, we know that is only symbols without meaning. So it means the syntax only defines the rules how I can construct well-formed and valid sentences of symbols within my logic. So whenever we look at syntax, it means this is the way how I create logical statements, logical expressions, and how they make sense, what is allowed, what is not allowed. They don't say anything about the meaning of that. This is defined by the so-called semantics, and the semantics defines, we know that, the meaning of syntax. So usually it defines rules how the meaning of complex sentences of symbols can be derived from atomic sentences of symbols. Therefore, of course, we also have to describe what's the atomic, what's the meaning of an atomic symbol. But how we do that, we will come back to that. So here, again, the term semantics becomes rather important. So as an example, when I have a statement in a programming language like that one, you see here, if I is smaller than 0, then display negative account, exclamation mark. So this would be a program line, and of course this has some meaning. It means print the message negative account if the account balance is negative. So you see here assignment of meaning is rather important. But only here, of course, it's only an informal semantics because we describe what it means with natural language, which cannot be processed in an automated way with a computer. So you need further complex analysis to interpret this informal definition. So therefore, we want, of course, to derive somehow a formal semantics of that. Okay, so the point is, as a computer scientist, so why should I care about semantics? Good question. So maybe I can't answer that, but of course I can get help from some famous people in history. So maybe you know Bertrand Russell, one of the most famous philosophers here from the 20th century. And he was also a great logician and mathematician, and he can give an answer why we should care about semantics. So he would say, for example, well, from a philosophical point of view, we need to specify the relationship between statements in the logic and the existential phenomena they describe. Sure, yeah. But you would say, for example, yeah, that's okay, but I don't get paid for philosophy. Yeah, but also Mr. Russell has an answer for the practical persons amongst us. He would say, from a practical point of view, in order to specify, build, and test ontology-based tools or systems, we need to precisely define the relationships, like, for example, entailment relation, between logical statements, and this defines the intended behavior of tools and systems. Sure, so we need semantics simply to define these relationships and to define the intended behavior of things. This is then the so-called intended or intentional semantics. So this is quite important. So let's have a look at different variants of semantics that exist. So the first of all, again, we have here an example of programming language here, the computation of factorial in some programming language is given. And of course, the intentional semantics of the program code you see here. So there is a function defined, and then, of course, there is the definition how it really works. And the point is, this is the computation of the factorial. And of course, if I simply write it in that way, it's the so-called intentional semantics. So it's the meaning intended by the user who has really written that part of code. So usually the intentional semantics restricts the set of all possible meanings, the set of all possible models, as we call the meanings here, to the meaning intended by the human user. That's the so-called intentional semantics. You distinguish this intentional semantics from the so-called formal semantics. So I can also give a formal semantics of that programming code, and then I see here, yeah, of course, this is the computation of the factorial in mathematical notation. So this means mathematical notation is kind of a formal language. So the formal semantics aims to express the meaning of symbol sequences here. These are programs in a formal language, and that should be in a way that assertions over the symbol sequences, it means over the programs, can be proven by the application of deduction rules. So it can be formally and automatically proven. That's the use or the purpose of this formal semantics. So therefore, formal semantics for us also is rather important. We want to define a formal semantic somehow. And then for programming code, of course, there is also a so-called procedural semantics. And this, of course, is the behavior of the program at execution time. This means the procedural semantics defines the meaning of a language expression, so the program. And this is the procedure that takes place internally within the computer whenever the expression does occur. So we have different notions of semantics. We have the intentional semantics, we have the formal semantics, and we have the procedural semantics. So definitely we want to have a formal semantics if we define the semantics of logic. But how to do that? So the question is, how do I define the semantics of a mathematical logic? So let's ask again Mr. Russell. Yeah, and Mr. Russell is quite right. He says, in mathematical logic, we define the semantics in terms of models. So with the help of a model theory. And a model is nothing else, or a model is supposed to be an analog of or a part of the world that's being modeled. So model-theoretic interpretation is that we try to interpret or we try to define the semantics with the help of a model of the things. And the model, of course, has the property that it's always simpler than the reality we want to express with the help of the model. So we interpret logics with the help of a model. And the one who introduced that was Alfred Tarski, who already in the 1920s as a young man defined model-theoretic semantics. He said, model-theoretic semantics performs the semantic interpretation of artificial and natural languages by identifying meaning with an exact and formally defined interpretation with a model. So he says the meaning or the semantics of a statement in a natural or an artificial language like logic is nothing else than the formal interpretation with the help of a model. And as we said, a model always is simpler than the real world thing we want to model with it. So therefore, it's easier to derive also the meaning. So let's look at a more specific example. So here, for example, the model-theoretic semantics of propositional logic. What's that? Propositional logic, we all know that it's the simplest kind of logic, and there we have truth values which are connected by simple connectives, and the interpretation or the semantics of propositional logic is rather easy. So what you do is you assign truth values to atomic assertions, to variables or assertions you have there, so they can be either true or false. And then when they are connected with these logical connectives, you have truth tables which define how these logical connectives, which are and, or, implication, or equivalence, how they work. So this is done by truth tables. So this is a rather simple model-theoretic semantic. We assign truth values to atomic assertions, and we describe the working or the computation of logical connectives with the help of truth tables. This is quite simple. That's a model. That's model-theoretic semantics. And in that way, we can also define a model-theoretic semantics for the more complex first-order logic. And we will also define a model-theoretic semantics for the description logics later on, which are the basis of our ontologies. Okay, so now let's generalize this for any kind of logic. So any logic L consists of first, usually a set of statements. So they are formed usually according to some kind of syntactic rules. So this is the syntax. And together with these statements, we have an entailment relation. So this is the relation which says how to deduce new facts from old facts, or new statements from old statements that are already there. So how is this entailment relation defined? So, for example, if we have here phi, which is a subset of our statements S, and we have small letter phi, which is an element of S, so which is a statement, then we can say small phi can be deduced or entailed from the set capital Phi. So small phi is a logical consequence of capital Phi, or from the assertions of capital Phi follows the assertion small phi. This is what the entailment relation says or can say. So therefore is it used. And the point is, if you have two assertions, phi and psi, which are both statements of S, of your set of statements, then if both hold, so for example, if from phi you can deduce psi, and from psi you can deduce phi, so here you have to see in the entailment relation, always on the left side there is a set of statements, so therefore if you have a single statement we have to write curly braces around that. And on the right side we simply derive one statement or entail one statement from a set of statements. And this set of statements usually then in our logic is also a knowledge base. Okay, so if one can be entailed from the other and vice versa, then both assertions, phi and psi, they are logically equivalent. These are the basic notions we have to keep in mind when we want to define new logics here. Okay, so that's the fundamental concept that is always followed. In the next part of the lecture, we will have a short recapitulation of the most simplest form of logic, of propositional logic.